Hello everybody, this video is going to be the introduction to our nuclear chemistry chapter. In part 1 we're going to learn some concepts, and then in part 2 of the video we're going to learn how to balance some nuclear reactions. So let's get started. So nuclear chemistry is the study of how the nucleus itself changes during a nuclear reaction. The normal chemistry reactions that we do in the lab involve the electrons. There's no change to the actual nucleus. So that's the big difference between what we do for almost all of the school year and this specific chapter. We've learned how to write symbols for our elements, but just a quick reminder. We're going to have our atomic number, the number of protons on the bottom, and our mass number on the top. It's important that we know how to write our symbols like this because when we do a nuclear reaction, we're going to be changing the number of protons and neutrons. So we do need to know how to show that in our equation using symbols like this. So I'm going to compare the difference between a typical chemical reaction and the nuclear reactions. So the first difference is in a normal reaction, it's the chemical bonds with the electrons that are being broken. During a nuclear reaction, the nucleus itself is either going to be emitting or maybe absorbing particles or energy. In a typical reaction, the atoms themselves remain unchanged, but you rearrange where they are in the molecules. For a nuclear reaction, you may actually be converting it into a totally different element. The name and the symbol may be changing. That's a very big difference. For a typical reaction, we only are interested in the valence electrons, the electrons that are on the outside of an atom. Whereas in a nuclear reaction, you could be changing all sorts of particles. Chemical reactions can absorb or release energy, but compared to a nuclear reaction, it's a very small amount. Nuclear reactions, if you think about something like, nuclear power plant or an atomic bomb, right? There's huge amounts of energy being changed. In a chemical reaction, you can change the speed of the reaction by changing the temperature. Maybe you grind it up into a smaller sized particle. Maybe you increase or decrease the concentration. But in a nuclear reaction, you're not going to be affected by all of those. The rate is inherent to the reaction that's taking place. Changing the temperature is not going to change your reaction. So when we're doing our nuclear reactions, we're looking at isotopes a lot. So you want to make sure that you're thinking about which isotope of something you have, be comfortable with that phrasing. Changing the nucleus itself, large amounts of energy, right? Those are the big deals here. We use nuclear reactions for things. We don't want an uncontrolled nuclear reaction. That's dangerous. But if you can control it and use it properly, they can be very useful. So things like power plants, we use it to track chemical reactions in biological processes. We can essentially use a radioactive substance and see how it travels through the body in different metabolic pathways and things like that. We use radiation therapy for cancer, where we can try to kill the cancer cells and hopefully leave the healthy cells alone. We even use it to determine how old things like fossils are or rocks. If you ever learned, about dinosaur fossils and things and how they know how old they are, it's by using nuclear reactions that take place. So there's kind of different types. We have fission reactions, where you're splitting a nucleus into more parts. Fission, right? We're splitting it. These can set off chain reactions. When an atom releases particles, those particles can bump into another atom, which, starts that one releasing particles, and then those particles bump into more atoms. So you can kind of get a chain reaction happening. In a nuclear reactor, what they're doing is they're trying to prevent that chain reaction from getting out of control. They're trying to contain it and have it, proceed in the way that they want it to. If it gets out of control, that's when you get things like a nuclear meltdown or something, right? Here's a picture of nuclear fission, kind of a cartoon picture. You can see here how it starts with one particle, and when it breaks apart, it releases more particles, which can hit other elements. Sometimes nothing happens, but sometimes that might set off another one, and it can just continue and grow and grow and grow. So everybody always seems to want to ask questions about kind of how long have we been doing this? When did we start? Well, our first controlled nuclear reaction was 1942. And then, we have things like atomic bombs and power plants and stuff ever since then. Fusion compared to fission, fusion is when we're combining our nuclei together. This does not typically happen. If you think about the charge inside the nucleus, positives and positives don't want to be smushed together, do they? And so it's not something that is going to necessarily occur in a more natural way. We typically have to force it to do that. Fusion, if we could get it to work, would be very inexpensive compared to fission. There would be less or no radioactive waste. The problem, though, is that this can be hard to control. It takes a lot of energy to get it started, and we just have not been able to do it in a way that is in a controlled power plant type setup. But there's a whole branch of science of people trying really hard to come up with fusion power plants. If they could do that, that could be a real game changer for our, energy issues. We see that happen in things like stars, the hydrogen bomb. Obviously, that's not a nice controlled, situation. And then we're hoping that someday we'll have power plants that can do this. So we're going to talk about the stability of different types of particles here. So when we're looking at our elements, some of our elements are very stable. Some are what we call marginally stable, and some are unstable or radioactive. And it's going to have to do with the ratio of protons to neutrons. There's better ratios and worse ratios. So the atomic numbers 1 through 20, those elements are all very, very stable. They tend to have a 1-to-1 ratio of protons to neutrons. So for example, carbon-12, nice even ratio, very stable. As your numbers start increasing, we start seeing an imbalance in the ratio. So atomic numbers 21 to 82, we start having more of a 1 to 1.5 ratio. For example, if you look at mercury 200, do you see how many neutrons that has compared to protons? The nucleus starts having a hard time holding on to all those particles. And so it starts to become a little bit unstable. The very large elements are going to be even larger ratios. And they become very unstable, very radioactive. Sometimes they're only man-made. They don't exist naturally because they're so unstable. Sometimes they have a very, very short lifespan before they break apart into other particles. So the stability really has to do with this ratio of protons to neutrons. So let's talk a little bit about that. So if you think about the nucleus, we should have the nucleus being repelled from itself. It's filled with protons. It's cram-packed with these positively charged particles, which should want to repel. And they don't. They don't just randomly fall apart. And so the thing that holds them together is a force. We've heard of other forces like gravitational force, right? Well, there's one called strong force. Strong force holds the nucleus together, even though those protons want to repel each other. as you start to increase your number of neutrons, it's like a rubber band that's being stretched too far. Eventually, there's not enough force to hold them together. And when that happens, the particles are going to go flying out of that nucleus, right? So when you start increasing those neutrons, when you start deviating from that 1-to-1 magical ratio, then you start getting more radioactive, which means you're more likely to have the nucleus fall apart into smaller pieces. We can graph the stability of our elements, and we find an interesting little pattern when we look at it on a graph. This green area, this is called the band of stability. The elements with these ratios of protons to neutrons inside this green band tend to be more stable. Up here, do you see this little blob? We call that the island of stability. We don't really know why it's kind of set off by itself. There are people who are researching just things inside this island. There are people who are looking to see if we can find another island of stability somewhere else as well. The red line is a perfect 1-to-1 ratio. And you can see in the beginning, 1-to-1 is a nice stable ratio. And then our band of stability deviates a little bit, right? We start deviating from that 1-to-1. So it's an interesting thing. Learning about something like strong force is a pretty complicated topic. We're not going to learn much more than this. This is kind of all we're going to learn about it. If I give you two isotopes and I ask you to predict which is more stable, you just find the one that's closest to a 1-to-1 ratio. Okay, that's the best guessing that we can do. Let's move on to the different types of radioactive decay particles that we can see. When an unstable element breaks apart, different types of particles can be released. The first type of particle is called an alpha decay. An alpha particle is 2 protons and 2 neutrons stuck together, which, if you think about it, is the same as a helium atom, right? A helium has 2 protons and 2 neutrons. The difference between a helium particle and an alpha particle is the alpha particle has no electrons. It's just the nucleus part. Here's an example of a nuclear reaction. We have uranium that is unstable. That poor little nucleus is just not stable. The ratio here of protons to neutrons is terrible. The strong force is not strong enough. It can't hold on. What it's going to do is it's going to spit out an alpha particle. It's going to release 2 protons and 2 neutrons in an attempt to get that nucleus smaller. The particle that you start with is called the parent. The element that you make at the end is called a daughter product. And this is our radioactive particle. Radioactive particles are dangerous because they're coming out very, very high speed. And so if they hit you, they can cause damage to your cells, right? That's why they're dangerous, is the speed at which they're being emitted. We typically see alpha decay in very large nucleuses, right? Larger particles will try to do this to try to shrink that ratio down a bit. The smaller they can make that nucleus, the more stable they'll be. Here's just a summary of some information about alpha particles. We don't want to say that it's a helium element, right? We need to specify that it's the nucleus. You have a couple different options for writing the symbols. You can write it with a helium symbol, or you can use the fancy alpha symbol. The atomic number we always put as a 2, and the mass is a 4, because there's 2 protons and 2 neutrons, so our mass ends up 4. The charge, however, is not neutral. Even though we use a helium symbol, this has a charge of +2 because there's no electrons. 2 protons, No electrons, you get a +2 charge. If you use a piece of paper or clothing, like if you have a shirt or something on, the alpha particles can't go through it. So even though they can be dangerous, they are, slower moving than the other particles, and so you can stop them with something as simple as a piece of paper or wearing a shirt. Let's move on to the next type of decay. We're going to do beta particles next. So a beta particle is what happens when an unstable nucleus emits a particle that looks like an electron. The thing is, it's not exactly an electron because it is not coming from the orbitals. It's coming from inside the nucleus. We're going to break something apart into smaller pieces, and one of those pieces looks just like an electron. So what happens is we take a neutron, we smash the neutron into pieces. One piece is a proton and one piece is an electron. We don't typically think about neutrons or protons being able to be divided up further, but they actually can. So the nucleus converts a neutron into this beta particle and into a proton. And that helps because that increases the number of protons present. And so that fixes that ratio of protons to neutrons a little bit. The beta particle is not going to stay inside the nucleus. The proton stays, but the beta particle is released. That comes flying out at us. That's the radiation that we see. So here's the summary chart. It's basically an electron. I just really want you to understand that it is not coming from the orbitals. Okay, that's really important. Charge is -1, just like a electron. It's super tiny, right? So it's basically 0. They're going faster, okay? They're smaller than an alpha particle. They're going a little bit faster than an alpha particle. So they can go straight through the paper and straight through your clothing, but they could be stopped by something like a piece of aluminum foil. So they're more dangerous, but you can still stop them somewhat easily. Here's another type of decay called a positron. If you look, this is a very similar symbol to the beta particle, except it's a plus sign, isn't it? It's just like a beta particle, same size and everything, except instead of negatively charged, it's positively charged. So let's look at where this comes from. Similar to the beta particle, what we're doing is we're going to smash something into pieces, okay? So instead of a neutron becoming a proton, this is opposite. A proton is going to turn into a neutron. So we take a proton, divide it up into different pieces. The neutron stays inside the nucleus. The positron gets spit out towards us. Next type of decay, gamma. Gamma emission is the more deadly kind, the more dangerous kind. It's incredibly high energy, okay? There's no actual particles, there's no protons or neutrons or anything that we're counting up. It's just literally energy. So there's no actual particles other than these photons that are coming at us. Usually gamma is happening while other types of particles are being released. So it can be by itself, but we often see it happening in addition to other types of radiation. We use this funny little symbol, right? This gamma symbol. You might see people use a little squiggly line trying to represent that it's that high energy that's coming out. If we look at the summary chart for this, you can see there's no charge, there's no mass, it's just energy. In order to stop this, you have to have something like lead or concrete. If you ever learned about in World War II, they were building, fallout shelters and things. They were either lined with lead or they had very thick concrete walls. If you ever go to the dentist and get x-rays, they put a lead drape over you, like an apron over you made out of lead to stop any radiation that's coming at you. It is a little bit interesting that we still do that because the x-rays have been improved so much that you would have to have so many x-rays. You'd basically have to do nothing but get x-rays in order for it to be harmful. They've really improved the technology, but they understand that people are nervous about radiation. We don't really, a lot of people don't understand it. And so they put that lead drape on you, even though getting an x-ray at the dentist is probably not going to hurt you, right? So it's kind of just the illusion of safety that they're trying to provide because they understand that not everybody has learned about radioactive particles and which ones are harmful and which ones aren't. So it's kind of an interesting little thing to learn about. All right, so now that we've learned about the different types of particles, we are going to start balancing some equations. It's very similar to how we balance normal chemical reactions. We just have to count all the particles on both sides. The difference here is that we're not just making sure the atoms balance, we have to make sure the protons and the neutrons balance. So what we're going to do is we're going to be counting up the numbers on each side and making sure they match. One thing that's tough is that the actual symbol, the name of the element might change. If you lose 2 protons, you're not going to be in uranium anymore, right? So you may have to change the name and the symbol. We're going to get all the numbers and then you can worry about the symbols. So let's look at some examples. Write the nuclear equation for the radioactive decay of polonium-210 by alpha emission. So step 1, you're going to write the element that you're starting with. Remember that we're going to put the atomic number on the bottom and the mass number on the top. They told you it was polonium, so you look at your periodic table, you find polonium, and that tells you you have 84 protons. The 210 came from the problem up here. Remember, you may have different isotopes than the ones on the periodic table, so you need to make sure that you use whichever isotope the question told you. If they just told you polonium, then you can use the isotope that you see on the periodic table. But if they tell you a specific isotope, make sure you use that isotope. Next, this is a decay, which means that this particle is breaking apart. So this is my reactant. Now I'm going to put my arrow to show people what it turns into. It told me it was an alpha emission. Emission means it was released. It is a product. So I'm going to write my alpha particle. You need to put the 4 and the 2. If you'd rather use the fancy little alpha symbol, you can, but you still need to put the 4 and the 2. Now what we have to do is we have to figure out the missing part, okay? So what I'm going to do is I'm going to look and say, okay, I need this to add up to 84 on the bottom. On the right-hand side, I only have a 2. What number do I have to add to a 2 so that it will eventually equal 84? And I'm going to do the same thing on the top. I need to equal 210. So what am I going to add to the 4 over here so that this entire side ends up equaling 210? Well, I'm going to get an 82 on the bottom. 82 plus 2 equals 84. If I look at my periodic table and I find 82 protons, I find out that that's lead. I don't necessarily take the isotope number from the periodic table. I'm going to calculate it myself because it may be a different isotope than normal. What do I add to 4 to get 210? 206. So this is the daughter product. My polonium-210 released an alpha particle, and the piece that was left over is a lead atom. Remember, the name, the identity comes from the number of protons. All right, let's do another one. Why don't you try this one? Pause and give this one a try. All right, so step 1 was to write what we're starting with. I'm starting with radium-226. Please be careful not to mix up radium and radon. That happens a lot. Be careful. Now I'm going to put an arrow because particles are being released. It is emission. This is turning into something else. They told me an alpha particle was released. Now I'm going to find my missing pieces. So 2 plus 86 will equal 88. If I find 86 on the periodic table, I'm going to see that it's not radium anymore, it's radon. 4 plus 222 equals 226. Now, just like in math class, if you put this part first and the helium particle second, it doesn't matter. 1 plus 2 and 2 plus 1 gets you the same answer, right? So the order in which you write your particles does not matter. Where you write the numbers for each particle matters. If you flip this or you flipped this, that would be wrong. If you wrote the helium and the radon on the left and you put the radium on the right, that would be wrong. So just be careful about those pieces. All right, let's try a beta decay this time. This time we have zirconium-97. It's going to release a beta particle. We're going to start the same way. I look on my periodic table and I find out how many protons does zirconium have. Okay, it has 40 protons. The question told me it was the isotope 97, so a 97 mass goes on top. This is a decay, it's falling apart. Beta particle is released. You can either use the E, or if you'd like to use that fancy beta symbol, you can, but you need a 0 for the mass and a -1 down here. Now that sounds a little bit weird because we think of this as the number of protons. How can you have a -1 proton? Well, remember that you are converting a neutron, right? You're smashing that neutron into a proton and into a beta particle. And so that -1 down there is going to help us account for that fact. So it's a little bit weird to think of it as a negative number, but you'll see why that works with our math in a minute. Now what I have to do is figure out my missing particle. What do I add to -1 so that it equals 40? 41, which makes sense that my proton number increased by 1 because I smashed that neutron up, right? A neutron turned into a proton, so this should go up by 1. So the reason we put a -1 here for the beta particle is because that will help us make sure our particles are conserved mathematically. That way we're realizing that this is not magically increasing. Okay, it came from somewhere. -1 plus 41 equals 40. So I look on my periodic table, I find out which particle has 41 protons. I find out that it's not zirconium anymore, is it? It's now niobium. What do I add to 0 so that it equals 97? 97. The mass isn't changing here, okay? The neutron turned into a proton, so that mass was conserved. So that's why the mass number doesn't change, but the proton number does. We lost a neutron, we gained a proton. All right. Sometimes we're going to ask you to figure out not the element that is made, not the daughter product, but sometimes we're going to ask you to figure out what the type of radioactive decay was. But it's the same exact process. You're just finding the missing piece. So start with your carbon 14. If you notice, that's not the isotope of carbon that's on the periodic table, is it? Carbon 12 is on the periodic table because that's the most abundant, most stable, that's the average, right? Carbon 14 is a little bit more radioactive. It has too many neutrons. Now I'm going to draw my arrow. Now this time, instead of drawing the decay particle, I'm going to draw nitrogen 14 because that's what they told me I had. Nitrogen has an atomic number of 7. It told me it was the isotope 14. I'm going to put a 14 up here. Now I have to find the missing piece. What do I add to 7 so that it will equal 6? Minus 1. What do I add to 14 so that it equals 14? 0. A 0 and a minus 1 tells me that it's a beta particle. I took a neutron, I smashed it apart, I got a new proton that wasn't there before, and I've released this beta particle out of the nucleus, out towards us. Okay. Now sometimes these get a little bit more complicated. Sometimes instead of releasing a particle, you may be absorbing a particle. Sometimes that's called bombardment. You might be hitting it with something. You're bombarding the original isotope. Sometimes you have more than one particle being released at a time, but it is all just simple algebra, okay? So let's look at this horrible looking problem. I have 2 neutrons that are hitting a uranium atom. It's going to break apart, it's going to release 3 beta particles, and we're going to be left with 1 daughter product over here. All we have to do is keep track of the numbers, okay? So over here, 2 neutrons on top, 2 times 1, plus my uranium mass. Okay, so the entire top part over here should equal 237. On this side, well, 3 times 0, that's 0, plus 237. Look, those match, don't they? Good. On the bottom, 2 times 0 plus 92. The bottom on both sides should equal 92. So let's try this over here. 3 times negative 1 plus 95 is 92. So you can see that even though we have a little bit more complicated pieces happening, it still is just equaling on each side. Some people would rather rewrite this and literally write 2 neutrons next to each other, and they would rather write 3 separate beta particles. But that's going to take you forever. It's going to take a lot of space. It's going to slow you down. And I would start being concerned that you might run out of time. So I would practice it like this. This is typically the way we like to do these problems. This, by the way, you see how these neutrons are hitting the uranium? That's called neutron bombardment. We are hitting the uranium with those neutrons, bombarding them. Let's look at another complicated one. Why don't you try to do the same thing I just did, where you find out what the top should equal on both sides, and you should see what the bottom would equal on both sides. You can pause if you need more time. All right, so 0 plus 218 should equal 218. Now look at this side. 218 plus 0 is 218, so those both match. On the bottom, negative 1 plus 85 will be an 84. And on this side, 84 and 0 is 84, so those match perfectly. This, do you see this time? We're absorbing this electron, or sorry, this beta particle is being absorbed. That's called electron capture. So sometimes they're going to have fancy names for these things. You'll just kind of learn that as you do practice problems. Sometimes we may throw out a particle you've never seen before, but if you understand the concept that everything has to be conserved at the end, then you're fine. You'll be able to do any problem we give you, no matter how many pieces it has, no matter how, weird the particles get. As long as you can make the numbers equal on both sides, you're good to go. Okay? All right, everybody, that was it for this lesson. I hope that was helpful. Bye.